Swayam Prabha. Digital India. Educated India.
In the first order case, we evaluated the response by solving for the differential equation sort of from scratch. In the second order case, we used what is known as the characteristic equation. Okay, now these two are linked, and in this lesson we will see the link between two. First, let me consider a first order system, although in this lesson the focus is on the second order system. So again, we can take this circuit as an example of a general first order system. Okay. Now, in this case, the differential equation for Vc is given by this, and the natural response is evaluated by solving for the source free case. Okay. Now, if you assume that Vc is some exponential p times t, okay, substituting it in here, we get Rc times p times exponential pt plus exponential pt equals 0. And we can have a coefficient V0 here, and that doesn't change anything. V0 appears in both places. Now this will be identically equal to 0 only if this multiplying factor of the exponential is 0. So this part has to be equal to 0, or in other words, p is minus 1 by Rc. Okay. So we get the result which we are already very familiar with, that the natural response is some V0 exponential minus t by Rc. So this is the characteristic equation. And the root of the characteristic equation P is minus 1 by Rc, and it has dimensions of frequency. This is as you expect, because the argument of the exponential is p times t, which should be dimensionless. So p has dimensions of 1 over time or frequency. Okay. Then we see that the time constant in a first order case, the time constant tau, which is Rc, is minus 1 by p. Okay. Minus 1 over the root of the characteristic equation. So we can use this in general for higher order equations also, as we did for the second order equation. We've already found the solution to the second order equation. Here I am trying to relate it to the first order case so that we get some more insights into our solutions. Now in a second order case, we have a second order differential equation. Let's say this is the differential equation in the relevant variable. Now for the natural response, the right hand side is substituted with 0. Okay, so I won't worry about it. And I have normalized the left hand side so that the coefficient of Vc is 1. Okay, this is just for convenience. Now this second order equation can be written as a combination of two first order equations. So That is, we go from the input to some variable Vx and from there to Vc. Now it is easier to understand in a picture. So let's say we had a second order system with some Vs as the input and Vc as the output. We can think of it as two first order systems, one after another, with Vs as the input and Vc as the output, and this intermediate output is called Vx. Okay, and for the natural response we set Vs to be 0. Okay, it turns out this kind of picture makes it convenient to figure out the nature of the solution in this case as well. Okay, so the characteristic equation here, if you assume a solution of the type Vc is some V0 exponential pt, the characteristic equation would be a2 times p square plus a1 times p plus 1 is 0. So every derivative term will have a p and nth order derivative will have p to the n. Now the characteristic equation of this is b1 times p plus 1 is 0, and this is b2 times p plus 1 is 0. Now this has some roots p1 and p2. It has two roots, okay, because it's a second order equation. Now this has a single root. P1 is minus 1 by b1, and similarly this has another root. P2 is minus 1 by b2. So the two roots of the characteristic equation now become, one of them is the root of this and the other one is the root of that one. Okay. Now if you combine these two into the second order differential equation, you have to get exactly the same coefficients. In a circuit with real components, these coefficients will be real. Okay, but these two need not be real because this Vx refers to some fictitious output which is not really accessible. So these could be real, but could also be complex conjugates. Okay, so both these possibilities exist. That we know already from the second order equation, that this can have roots which are real and distinct, real and identical, or complex conjugates. Okay, now remember, b1 and b2 will not be some arbitrary complex numbers, they will be complex conjugates because the eventual equation has only real coefficients. So the two solutions p1 and p2, if they are complex at all, will be complex conjugates of each other. Okay, so what does this mean? If you think of this as a cascade of two first order systems, and let me consider first the natural response. Okay, so that is the input is 0. Now the first one here had a characteristic equation b2 times p plus 1 is 0. So this p2 is minus 1 by b1. Okay, now the natural response of this would be just exponential p2t. Okay, now if you think of the second first order system, it is being driven by an exponential. Okay, I will omit the scaling factors everywhere, okay, because I just want to point out the nature of the solution. So now the solution here is the response, the total response to an exponential input. Okay, the input to the second block is exponential p2 times t, and this has a characteristic equation b1p plus 1 equals 0, whose root is p1 is minus 1 by b1. Okay, so the force response of this consists of its natural response as well as the input exponential. Okay, now let's assume first that p1 and p2 are distinct and real. Okay, if they are distinct, they will be necessarily real. Then this will consist of, first of all, the input exponential scaled by some value. So it will have something times exponential p2t plus its own natural response, which is something times exponential p1t. Okay. So the natural response of the first stage is the driving input to the second stage, and that also appears as it is. Now let's imagine a second case where P1 and P2 are real and identical. Okay. This happens in the quadratic equation when A2 square is 4 times A1. Okay. So then what happens is this P1 and P2 are both identical. So the output here, which is the natural response of the first order system, is exponential P1t, because P2 is the same as P1. We know that when a system is driven by its own natural response, the output will be of the form A1 plus A2t times exponential P1t. It will get multiplied by this t, which grows with time, because a system has a certain natural frequency. If it's excited by its own natural response, then the multiplying factor tends to blow up over time. Okay. So this gives you the idea that the solution in this case is of the form A1 plus A2t exponential P1t. There is only one P1, P2 equals P1. In the other case, it is A1 exponential P1t plus A2 exponential P2t. And finally, when P1 and P2 are complex conjugates, okay, then also it's the same as the distinct and real case, except that P1 and P2 are related in some way. Now remember, here the output will be exponential P2t, which is a complex number really, but this is some fictitious case. This is not an accessible point in the circuit. We have just mathematically split up the second order system into two first order systems. But here you will get exponential P2t plus exponential P1t. So we will have A1 exponential P1t plus A2 exponential P2t, and P2 will be P1 conjugate, which also means that A2 has to be A1 conjugate for a real solution. Okay. So that's how we get the different cases for the natural response of a second order system. Okay. Now let's consider the forced response, and let me again consider some exponential st as the input. Okay. So now you can imagine many different cases. First, I will take S is different from P1, which is also different from P2. Okay. So they're all distinct. So then at this point, what will we get? We get the total response to an exponential. So instead of exponential P2t, we would have got something times exponential st plus something times exponential P2t. And here we will get the input exponentials scaled by some number. So we will get something times exponential st plus something times exponential P2t plus the natural response of the second stage, which is something times exponential P1t. Okay. So the total response would be A1 exponential P1t plus A2 exponential P2t plus something times exponential st. And this something can be evaluated by substituting exponential st in the solution to the differential equation and solving for the resulting equation. Okay. Now similarly, if I have exponential st as the input when P1 and P2 are complex conjugates of each other, and I'll assume that S is not equal to either P1 or P2, we will simply get plus exponential st. And similarly, if the P1 and P2 are real and identical, but S is not equal to P1, we will simply get plus exponential st. But these are not the only possibilities. For instance, in this case, I could have S equals P1 or S equals P2. So if S equals P1, we will get A1 plus A3t times exponential P1t. Okay. Plus exponential P2t. Similarly, if S equals P2, we will have this coefficient of t multiplying exponential P2t. Okay. And similarly, in this case, in the second case, P1 and P2 are already identical. If S happens to be equal to P1, then we will get A1 plus A2t plus A3t square exponential P1t. Okay, so we get a t square term as well. And finally, in this case, it's possible that S is equal to either P1 or P2. And again, we have the same case as here. Okay, we could get A1 plus A2t exponential P1t plus A2 exponential P2t and so on. So there are many different possibilities. Now, I'm just going to only qualitatively outline all these other exotic possibilities. Finally, when it comes to force response of more complicated systems, we will not be evaluating them in a general way. We can do that by using exponential ST, and later, after you learn about Laplace transforms, you will see that any signal can be represented as an integral of exponential ST over S over different frequencies. That will let you solve the equations more generally. In our case, we will only consider the DC input case and the sinusoidal input case. In the sinusoidal input case, it turns out can be solved much more easily without even writing down the differential equation. That will come to later. Okay, but this should give you an idea of the nature of the solutions when you have a second order system. Mainly, you can have two separate exponentials with real frequencies P1 and P2, or you can have A1 plus A2t times exponential P1t, and finally you can have this case where you have complex conjugates which will eventually add up to some sinusoids. Okay.